We are asked to calculate the pH of a solution. We first want to ask ourselves, what's in the beaker? Is it a weak acid, weak base, strong base, or buffer? Because that will determine the type of calculation we do. Looking at the question statement, we see we have acetic acid, which is a weak acid, and we also have in solution the acetate ion, which is the conjugate base of that weak acid. We look at the relative amounts and see that we have 0.5 molar of each of these, so we have equal and high concentrations of a weak acid and its conjugate base. Therefore, we have a buffer. Now, with a buffer, we can actually solve it as if it was a weak acid or a weak base problem, or we could use the Henderson-Hasselbalch, and I'm going to do both. First, I'll solve this as a weak acid problem. I've written out the reaction of a weak acid and water. We initially start with 0.5 molar of both our weak acid and its conjugate base. And we assume that the amount of H3O plus that we get from the autoionization of water is negligible. When any reaction proceeds, we're going to lose X of the HA, gain equal amounts of H3O plus A minus. So we have 0.5 minus X, and 0.5 plus X. We write our Ka expression, H3O plus conjugate base over HA at equilibrium, and input our values from the ICE table, our equilibrium values. Now we look to see if we can make an approximation that will simplify our math. We multiply K times 1,000 and compare it to our initial concentrations from which we will either be subtracting or adding X. And in either case, that concentration value is much larger than 1,000 times Ka. Our approximation is therefore okay. This simplifies our math. So our 0.5 plus X reduces down to 0.5. Our 0.5 minus X reduces down to 0.5. And therefore, we see that 0.5 cancels out, and X, which is equal to our H3O plus ion concentration, is equal to Ka. And that means our pH, which is the negative log of H3O plus ion concentration, is equal to pKa. This is a general result for all balanced buffers. Balanced buffers are buffers in which the concentration of the base is equal to its conjugate acid. And the general result is that pH is equal to pKa in those situations. So we input our value of Ka, and we use 2 sig figs in our final answer. So there's 2 digits after the decimal point. So our pH is going to be 4.74. Let's summarize this problem. We first recognize that what we have in solution is a buffer because we have relatively high and equal concentrations of a weak acid and its conjugate base. We are solving this as if it were a weak acid problem. So we have some amount of our weak acid and some amount of its conjugate base already present in solution. And we can solve this as a typical weak acid problem and end up with a result of pH is equaling to pKa, which in this case is 4.74. Next, we'll solve this using Henderson-Hasselbalch, and you'll see it's much quicker. This solution is a buffer. It contains relatively high and equal concentrations of a weak conjugate acid-base pair. In this case, it's a weak acid and its conjugate base. Therefore, we can use the Henderson-Hasselbalch equation to determine pH. And now we substitute the relevant quantities. Okay, we look at the math and we see that we're taking the log of 0.5 divided by 0.5, which is the log of 1 equal to 0. So this entire part here goes to 0. And we end up with pH is equal to pKa, which is true for any balanced buffer. And when we do the math, we find that pH is going to equal positive 4.7447. Taking into account sig figs, we use 2 decimal places. And our final answer is that the pH is 4.74. The same result we got by solving this problem as a weak acid problem, but we got there a lot faster.